There is a spot in the night sky, near the handle of the Big Dipper, that looks empty. If you were to go out on the darkest night, in the middle of the ocean, far from any city lights, and look up at that spot with your naked eye, you would see nothing. Just a patch of black velvet between the stars. If you took a pair of binoculars and looked, you would still see nothing. If you took a powerful backyard telescope and aimed it there, you would still see nothing. For all of human history, we believed that this tiny patch of sky, no bigger than a grain of sand held at arm's length, was a void, a place where the universe was silent, a gap in the fabric of creation. But we were wrong. We were wrong because we were looking through an ocean. We were looking through the thick, turbulent blanket of the Earth's atmosphere. To see the truth, we had to rise above the air. We had to build a machine, polish a mirror to an impossible smoothness, and float it in the cold silence of the vacuum. And when we finally did, when we finally opened that mechanical eye and stared into the nothingness stared back. It wasn't empty. It was full. It was screaming with light. That grain of sand contained thousands of galaxies, billions of worlds, trillions of stars, and light that had been traveling toward us since before the Earth was born. This is the story of the machine that took that picture, the Hubble Space Telescope. But before it became a legend, it was a tragedy. Before it showed us the face of God, it was the biggest mistake in the history of science. This is the story of how we built a perfect mirror, launched it into the heavens, and realized it was blind. To understand why we needed the Hubble, you have to understand the frustration of the astronomer. Imagine trying to read a book while lying at the bottom of a swimming pool. The water is constantly moving. The letters on the page dance and shimmy. They blur together. You can see the book, you can see the words, but you cannot read the story. That is what it is like to look at the stars from Earth. We live at the bottom of an ocean of air. The atmosphere is a chaotic, fluid thing. It has pockets of hot air and cold air. It has winds and currents. As starlight travels through this ocean, it gets bent, it gets twisted. That is why stars twinkle. To a poet, a twinkling star is romantic. To an astronomer, it is a nightmare. The twinkle is the data being destroyed. The twinkle is the universe hiding its secrets. For centuries, men like Galileo and Newton dreamed of a way to stop the twinkling, but it was a man named Lyman Spitzer who dared to suggest the impossible. In 1946, more than 10 years before the first satellite, Sputnik, was even launched, Spitzer wrote a paper. He proposed a large space telescope. He argued that if we could put a telescope above the atmosphere, above the rain and the clouds and the shimmering heat, we could see things no human eye had ever seen. We could see the ultraviolet light that the atmosphere blocks. We could see the sharp, crystal clear geometry of galaxies. It was a dream of absolute clarity. But in 1946, it was science fiction. We didn't have rockets big enough. We didn't have computers. We didn't have digital cameras. Spitzer spent his entire life lobbying for this dream. He walked the halls of Congress. He talked to generals and politicians. He waited while technology caught up with his imagination. 40 years. He waited 40 years. And finally, in the 1970s, NASA said yes. The project was a monster. It was named after Edwin Hubble, the man who discovered that the universe is expanding. It was designed to be the most complex machine ever built by civilians. A school bus-sized satellite, packed with 5 scientific instruments, powered by the sun and controlled by computers that could lock onto a dime from 200 miles away. At the heart of the machine, the soul of the telescope, was the mirror, the primary mirror. It was a disc of glass, 2.4 meters, nearly 8 feet wide. But it wasn't just glass. It was ultra-low expansion glass, a special material designed to keep its shape even when the temperature swings from boiling to freezing in the vacuum of space. The company hired to build it was Perkin-Elmer a prestigious optics firm in Connecticut. They knew the stakes. This mirror had to be perfect. Not just good, not just industrial grade, perfect. The specifications were terrifying. The surface of the mirror had to be polished to an accuracy of 10 nanometers. It is hard to visualize a nanometer. Let's use a metaphor. Imagine the mirror was the size of the entire Earth. It stretched from New York to Tokyo, from the North Pole to the South Pole. If the Hubble mirror were the size of the Earth, the biggest bump on its surface, the highest mountain, would be less than 6 inches tall. It was the smoothest object ever created by human hands. The polishing began in 1979. It was a slow, meditative process. Day after day, year after year, the computer-controlled grinding machines rubbed against the glass. Grind, polish, measure, repeat. The technicians wore white suits. They worked in a clean room where the air was filtered to remove every speck of dust. A single flake of dandruff, a single eyelash falling onto the glass could ruin the surface. It was a temple of precision. They used a device called a reflective null corrector to measure the curve of the glass. It used lasers to map the surface, ensuring that the light would focus to a single, razor-sharp point. They worked on it for 2 years. Finally, in 1981, the polishing was done. The mirror was coated in a microscopic layer of pure aluminum to reflect the light, and a layer of magnesium fluoride to protect the aluminum. It shone like a pool of mercury. It was flawless. Or so they thought. They packed it away in a protective container. It was ready. But space is hard, and history is cruel. The launch was delayed. In 1986, the Space Shuttle Challenger exploded. 7 astronauts died. The space program ground to a halt. The Hubble telescope sat in a warehouse in California, a clean room tomb, costing the government millions of dollars a month just to keep it safe and dusted. It sat there for 4 years, waiting. The engineers checked the systems. They checked the batteries, but they never checked the mirror again. Why would they? It was the perfect mirror. It was done. Finally, the day came. April 24, 1990, the Space Shuttle Discovery roared off the launch pad at Cape Canaveral. Inside the cargo bay, wrapped in gold foil and white thermal blankets, sat the Hubble. The launch was flawless. The shuttle climbed the ladder of air, shook off the solid rocket boosters, and slipped into the smooth silence of low Earth orbit. 340 miles up, the cargo bay doors opened. The sunlight hit the telescope for the first time. The astronauts, Stephen Hawley among them, used the robotic arm to lift the telescope out of the bay. It was a tense moment. This was $1 billion baby. They released it. Hubble floated free. It looked majestic. A silver cylinder drifting against the blue curve of the Earth and the black depth of space. The solar panels unfurled. There was a glitch. One of the panels got stuck, but the astronauts fixed it. Mission Control breathed a sigh of relief. The hard part was over. The telescope was in the sky. Lyman Spitzer, now an old man, was watching. His dream was alive. The astronomers rubbed their hands. They prepared the champagne. They were about to see the universe in high definition. But first, there was the commissioning phase. Before the telescope could do science, it had to be focused. Just like a camera lens or a pair of binoculars, you have to twist the dial to make the image sharp. The engineers on the ground sent the commands, move the secondary mirror. The motors whirred silently in the vacuum. They picked a star, a simple star cluster called NGC 3532. They told Hubble, "Look at this star. Take a picture." The telescope turned. The gyroscope spun. The light from the star traveled down the tube, hit the primary mirror, bounced to the secondary mirror, and went into the camera. The data streamed down to Earth. It appeared on the monitors at the Goddard Space Flight Center in Maryland. The scientists gathered around the screen. They expected a dot, a pinpoint of brilliant light, a diamond on black velvet. The image loaded. Silence filled the room. It wasn't a point, it was a blob. It was a fuzzy, large spot surrounded by a misty halo. "It's just out of focus," someone said. "We just need to adjust the mirrors more." They sent new commands. Move the mirror up, move it down, tilt it. They tried for days. They tried for weeks. Every time, the result was the same. The stars were not stars. They were smudges. They looked like streetlights seen through a rainy windshield. The champagne remained corked. The mood in the control room shifted from excitement to confusion, and then to a cold, creeping dread. Something was wrong, fundamentally wrong. The engineers went back to the data. They analyzed the halos around the stars. They realized that the light hitting the center of the mirror was focusing in one place, but the light hitting the edges of the mirror was focusing in a different place. It is a condition called spherical aberration. It means the mirror is the wrong shape. They did the math. They calculated the error. The mirror was too flat at the edges. By how much? By 2.2 microns. A micron is a millionth of a meter. A human hair is about 50 microns thick. The error on the Hubble mirror was 1/50th the width of a human hair. It was an invisible mistake, a microscopic error. But in the world of optics, 2.2 microns is the Grand Canyon. Because of that tiny invisible shaving of glass, the telescope could not focus. It was nearsighted. The perfect mirror, the smoothest object ever made by humans, was perfectly wrong. The news broke. It was a disaster of biblical proportions. NASA had spent $1.5 billion. They had promised the public the wonders of the universe. They had promised to see the edge of time, and instead they had launched a blurry camera. The press was merciless. They called it the Techno-Turkey. They called it the Hindenburg in orbit. They called it Mr. Magoo. Late-night comedians made jokes about it. Politicians demanded hearing. They wanted to know who to blame. How could you spend that much money and not check the mirror? They screamed. The investigation revealed the tragedy. It wasn't the mirror polishers. They had done exactly what the machine told them to do. It was the machine, the reflective null corrector. The device used to measure the mirror during those years of grinding had been assembled incorrectly. A single bolt. A technician had inserted a bolt into the measuring device. He had painted over the end of the bolt with non-reflective paint, but a tiny flake of paint had chipped off. The laser hit that chip instead of the bolt. It threw the measurement off by 1.3 millimeters. Because of that 1 millimeter error in the tool, the mirror was ground perfectly to the wrong prescription. It was a tragedy of irony. The mirror was precisely, flawlessly incorrect. Back in space, Hubble drifted. It was alone. It was blind. The computer systems worked. The solar panels worked. It could point anywhere in the sky with incredible accuracy, but it couldn't see clearly. The scientists tried to use image processing software to sharpen the pictures. It helped a little. They could still do some science, looking at bright objects, looking at ultraviolet light, but the dream of seeing the deep universe, the faint galaxies, the beginning of time, that dream was dead. The mood at NASA was funereal. Some people said we should abandon it. Let it drift. Let it burn up in the atmosphere as a monument to failure. It seemed like the end of the story. But Hubble was not just a satellite. It was designed to be visited. It had handrails. It had doors that opened. It was built to be serviced by the space shuttle. And in the cafeteria at Goddard and in the offices at JPL, a whisper began to circulate. A crazy idea. If the telescope is nearsighted, can we give it glasses? Can we fly up there, catch it, and put a contact lens on a mirror? that is floating inside a tube in the vacuum of space. It had never been done. It would require the most complex spacewalks in history. It would require building a device that had to fit into the telescope with the precision of a Swiss watchmaker while wearing bulky gloves, traveling at 17,500 miles per hour. But it was the only chance. We had built a blind king. Now we had to heal him. In the darkness of orbit, Hubble waited. It turned its blurry eye toward the Milky Way. It saw the fuzzy lights of star clusters. It saw the smudged ghosts of planets. It listened to the commands from Earth, sensing the disappointment in the radio waves. It drifted in the silence, a billion-dollar joke. But help was coming. The repair mission was being planned. The astronauts were training in the underwater tanks. The engineers were building the glasses, a device with the terrible acronym COSTAR. The redemption of Hubble would not come from a computer fix. It would come from human hands. It would come from the touch of a glove on metal. But that is the story for the next part of our journey. For now, let us leave the telescope in the dark, spinning slowly, waiting for the light to become sharp, waiting for the moment when the blur would resolve into the face of the infinite. The stars are patient, and soon the eye would open. Space is usually described as a place of action. Rockets fire, thrusters burning, orbits decaying. But for the Hubble Space Telescope, space had become a waiting room. For 3 long years, from 1990 to 93, the telescope circled the Earth every 97 minutes. It was a wounded giant, a blind king. It was still beautiful to look at, a silver cylinder gleaming in the sunlight, its solar panels stretching out like the wings of a golden dragonfly. But inside, the light was wrong. The photons from distant galaxies were hitting the flawed mirror and scattering. The sharp points of starlight were turning into fuzzy, indistinct blobs. On Earth, the jokes continued. The late-night comedians were still laughing. But in the quiet labs of NASA, the laughter had stopped a long time ago. It had been replaced by a grim, steely determination. They were not going to let the telescope die. They were going to fix it. But how? The telescope is in low Earth orbit, 340 miles up. You cannot bring it down to the shop. You have to go to it. And you cannot just polish the mirror again. The mirror is buried deep inside the structure, wrapped in baffles and heat shields. You cannot touch it. So, the scientists came up with a different solution. If you have a nearsighted person, you don't perform eye surgery if you don't have to. You give them glasses. They decided to build a pair of contact lenses for Hubble. The device was called COSTAR, Corrective Optics Space Telescope Axial Replacement. It was a miracle of engineering. It looked like a telephone booth filled with delicate mechanical arms. At the end of each arm was a tiny mirror, the size of a coin. The plan was audacious. Astronauts would fly the space shuttle up to Hubble, grab it with a robotic arm, open the back doors, remove a piece of old equipment the size of a refrigerator, and slide COSTAR into the slot. Once inside, the mechanical arms would deploy. They would reach out and place the tiny coin mirrors exactly in front of the telescope's instruments. These tiny mirrors were ground to the exact reverse prescription of the main mirror's error. They would catch the blurry light, correct it, and send it into the cameras as a sharp image. It was brilliant. But it required the most difficult spacewalks in the history of human spaceflight. The device had to be aligned to within a fraction of a millimeter, and it had to be done by humans wearing clumsy, pressurized gloves floating in zero gravity, while the temperature swung from boiling to freezing every 45 minutes. December 2nd, 1993, the Space Shuttle Endeavour sits on Launch Pad 39B. It is night in Florida. The xenon floodlights bathe the white ship in a surreal, theatrical glow. The humid air clings to the cold skin of the external tank. Inside the cockpit, 7 astronauts are strapped in. They are the A-Team, the best hands NASA has. Among them is Story Musgrave. He is not your typical astronaut. He is a surgeon, a mathematician, a poet. He is the oldest man on the crew, bald, intense, with eyes that seem to look through things. He has spent years choreographing this mission. He knows every bolt on the telescope. He has practiced these movements in a giant swimming pool until his muscles remember the dance better than his mind. 3, 2, 1. Liftoff. The night turns into day. The roar of the solid rocket boosters tears the sky apart. Endeavour rises on a pillar of fire, turning the Florida coastline into a map of light. 8.5 minutes later, the engines cut off. The roar vanishes. The vibration stops. The pencil floats. They are in orbit. The chase begins. It takes 2 days to catch the telescope. Ideally, orbital mechanics is a science of curves, but when you are chasing a satellite, it feels like a hunt. The shuttle pilot fires the thrusters in short, sharp bursts. They climb the gravity hill, and then they see it, a bright star on the horizon that doesn't twinkle. It grows. It becomes a shape, a silver barrel. Hubble. It looks lonely. It is tumbling very slowly. The commander slows the shuttle. They creep up on the telescope from below. The cargo bay doors are open. The Earth is a blue ceiling above their heads because in space, orientation is relative. Swiss astronaut Claude Nicollier operates the Canadarm, the robotic crane. He moves the joystick with the tips of his fingers. The long white arm reaches out slowly, gently. The end effector, the metal hand, hovers over the grapple fixture on the telescope. Click, captured. Houston, we have a firm grip. Nicollier gently lowers the telescope into the cargo bay. He locks it onto a flight support structure. It is like putting a baby into a cradle. Hubble is safe, but the surgery hasn't started yet. The mission plan calls for 5 consecutive days of spacewalks, 5 days of working in the void, EVA-1. The preparation. Story Musgrave and Jeffrey Hoffman suit up. They float into the airlock. They breathe pure oxygen for an hour to purge the nitrogen from their blood, preventing the bends. The airlock depressurizes. The needle drops to 0. The outer hatch opens. Silence. Musgrave pulls himself out. He is floating in the cargo bay. Below him or above him, the Earth is rushing by at 17,000 miles per hour. He sees the coast of Africa, the golden sands, the blue water, but he doesn't look for long. He turns to the telescope. It is massive. Up close, it is a wall of silver foil. The job today is to prepare the site. They have to replace the gyroscopes, the devices that tell Hubble which way it is pointing. Musgrave moves with a distinct style. He doesn't thrash. He flows. He touches the handrails lightly. He knows that if he pushes too hard, he will fly off in the opposite direction. Newton's third law is the law of the land here. Every action has an equal and opposite reaction. He opens the access doors on the telescope. They are huge metal flaps. He works the bolts. He is using a power tool, a massive battery-operated drill designed for space. It turns slowly with high torque. Whir. The sound vibrates through his gloves, up his... It is the only sound he hears besides his own breathing and the static of the radio. They replace the gyroscopes. They close the doors. It is a warm-up, a rehearsal for the main event. They float back to the airlock as the sun sets. A sunset in space is not like a sunset on Earth. It is a sudden, violent event. The sun drops below the horizon and vanishes in seconds. The light switches off. The world goes from blinding white to absolute black. Musgrave works in the dark, lit only by the helmet lights and the cargo bay floodlights. It feels like working underwater in a deep cave. EVA-1 ends. Success. EVA-2, the solar panels. The next day, 2 other astronauts go out. Their job is to replace the solar panels. The old ones are jittery. They expand and contract too much in the sunlight, causing the telescope to shake. This is a brute force job. They have to unbolt the massive wings and install new ones. At one point, one of the old panels refuses to roll up. It is stuck. The astronauts have to jettison it. One of them stands on the robotic arm, holding the massive golden wing. It looks like a piece of a broken satellite. He waits for the right moment. He pushes it. The panel drifts away into the blackness. It tumbles slowly, flashing gold as it catches the sun. It will eventually burn up in the atmosphere, a shooting star made of expensive metal. They install the new arrays. They look pristine, taut, perfect. Hubble now has a steady power source. Its hands stop shaking. Now, it is time for the eyes. EVA-3, the heart transplant. This is the big one. Musgrave and Hoffman are back outside. Today, they are replacing the main camera, the wide-field planetary camera WFPC. They have to remove the old one, a wedge-shaped instrument the size of a grand piano, and install the new one, WFPC-2. WFPC-2 is special. It has its own built-in corrective mirrors. It doesn't need the contact lenses. It has the correction built into its own internal optics. It is the heavy lifter of the mission. Musgrave climbs up the telescope. He sets up his foot restraints. He opens the access doors. He grabs the handle of the old camera. Okay, I'm sliding it out. It slides on rails. It comes out smoothly, a massive black box floating in his hands. He has to be careful. If he bumps it against the telescope walls, he could damage the delicate insulation. He hands it off to Hoffman. They stow it in a box in the cargo bay. Then, they pick up the new camera. This is the moment. This box contains the future of astronomy. Musgrave guides it into the slot. It has to align perfectly. The electrical connectors at the back have to mate blindly. He pushes gently. He feels the resistance. He wiggles it slightly. Thunk. It seats. He turns the latch. It locks. It's in, he says. His voice is calm, but his heart rate monitor shows the truth. Inside the shuttle, the pilot checks the dashboard. We have a keep alive signal, he reports. The camera is getting power. The brain transplant is successful. Musgrave pauses. He looks down at his hands. His gloves are white, bulky, pressurized. Inside, his fingers are bruised. The work is physically exhausting. Every movement is a fight against the suit. But he looks up. He sees the Aurora Australis, the southern lights, dancing below the shuttle, green curtains of fire waving in the upper atmosphere. He takes a moment to breathe, to witness. He is a mechanic working in heaven, and pieces bore. EVA-4, the contact lenses. The next day, the most critical day, astronauts Thornton and Akers go out. Their job is to install COSTAR, the telephone booth. They have to remove another instrument, the high-speed photometer, to make room for it. This is the sacrifice. To cure the vision, they have to give up one of the sensors. The photometer is removed. Then they lift COSTAR out of its box. It is a black box, roughly the size of a refrigerator. But inside, the arms are folded up like a Swiss Army knife. Thornton holds it. It is heavy. Mass is mass, even in zero gravity. If she gets it moving, it will want to keep moving. She has to control the inertia. She guides it to the opening. The tolerance is incredibly tight. She slides it in inch by inch. The guide rails engage. It slides deep into the belly of the telescope. Click. It is home. Inside the box, once it is powered up, the mechanical arms will unfold. They will reach out into the light path. But the astronauts cannot see that happen. They just have to trust the math. They close the doors. They lock the bolts. The surgery is complete. EVA 5, the cleanup. Musgrave and Hoffman go out one last time. They replace some electronics. They install a magnetometer. They put thermal covers over some exposed metal. It is the final polish. Musgrave floats to the top of the telescope. He grabs the solar mast. He looks down the length of the silver tube. He pats it. "Good luck, baby," he whispers. He knows he will never be back here. This is the pinnacle of his life. He disconnects his tether. He floats back to the airlock. The hatch closes. The pressure rises. The mission is done. The next day, the release. Nicolia uses the robotic arm again. He grabs the grapple fixture. He lifts Hubble out of the cargo bay. He holds it high above the shuttle. The sun is rising. The light hits the silver insulation. It is blindingly bright. Hubble looks different now. It has new solar wings. It has new electronics. And deep inside, it has new eyes. The arm releases. The shuttle fires its thrusters and backs away slowly. Hubble hangs there in the blackness. It gets smaller and smaller. The crew watches it from the windows of the flight deck. They are exhausted. Their hands are raw. They smell of sweat. But they are smiling. "We fixed it," Musgrave says. But they don't know for sure. Nobody knows. The telescope needs time. The new instruments are warm. They have to cool down to operating temperature. The water vapor trapped in the metal needs to outgas, to boil away in the vacuum. It will be weeks before they can open the shutter. Weeks of agonizing waiting. January 1994. The Space Telescope Science Institute in Baltimore, Maryland. The mood is tense. The memory of the spherical aberration disaster is still fresh. The scientists are terrified. What if the mirrors are misaligned? What if CoStar doesn't work? What if they broke something else? The command is sent: open the shutter on WFPC2. Target M100. M100 is a grand design spiral galaxy. It is millions of light years away. Before the repair, Hubble had taken a picture of it. It was a blurry, foggy mess. You could tell it was a galaxy, but it looked like a cotton ball dipped in milk. The telescope turns. It locks on. The CCD sensors collect the photons. The data is beamed up to a relay satellite down to White Sands, New Mexico, and over landlines to Maryland. The image processing computers begin to churn. The scientists gather around the monitors. This is the moment of truth. If this fails, NASA might be finished. The Hubble project will be cancelled. The screen flickers. The image loads. First, the black background. Then the stars. They are points. Razor-sharp, needle-point diamonds. No halos. No fuzz. Then the galaxy. It fills the screen. The arms of the spiral are distinct. You can see the dust lanes. Dark rivers of carbon twisting through the starlight. You can see individual stars in the arms. You can see glowing nebulae where new stars are being born. It is crystal clear. It is perfect. The room erupts. People are cheering. Some are crying. Champagne corks are popping for real this time. Senator Barbara Mikulski stands up and declares, "The trouble with Hubble is over. The techno-turkey is dead. Hubble is reborn. It is no longer a mistake. It is the most powerful eye ever opened by humanity." The first images are released to the public. They are on the front page of every newspaper in the world. People stop on the street to look at them. For the first time, we are seeing the universe as it really is. We see the pillars of gas in the Eagle Nebula, the pillars of creation, giant towers of hydrogen, light years tall, being eroded by the ultraviolet wind of newborn stars. They look like stalagmites in a cosmic cave. We see the Hourglass Nebula, an eye staring back at us from deep space. We see planetary nebulae that look like butterflies made of fire. We see galaxies colliding, ripping each other apart in a slow-motion dance of gravity. Hubble becomes a rock star. It is no longer just a scientific instrument. It is an artist. It paints the universe in colors we can understand. It takes the invisible wavelengths, infrared, ultraviolet, and maps them into gold, blue, and crimson. It turns the cold, dark void into a gallery of masterpieces. But amidst the celebration, there is a question. Now that we can see, what should we look at? We have looked at the planets. We have looked at the famous nebulae. We have looked at the bright galaxies next door. But what about the background? What about the dark? The astronomers want to use the telescope to solve specific problems. They want to measure the expansion rate of the universe. They want to study black holes. But the director of the institute, a man named Bob Williams, has a different idea. He has director's discretionary time, a block of time on the telescope that he can use for anything he wants. He doesn't need approval from a committee. He gathers his team. I want to do something risky, he says. I want to point the telescope at nothing. Nothing, they ask. I want to find a patch of sky where there are no stars, no galaxies, no nebulas, just black space. And I want to stare at it. For how long? For 10 days. The staff is shocked. 10 days is an eternity. Hubble time is worth thousands of dollars a minute. To stare at a blank spot for 10 days seems like madness. It seems like a waste. What if we see nothing, they argue. We will be the laughingstock of this. Again, Williams holds his ground. We are explorers, he says. We don't know what is there. That is why we have to look. He wants to take a deep field image. He wants to drill a hole in the sky and see what is at the bottom. They begin to search for a target. They need a spot that is absolutely empty. They look at the star charts. They find a tiny patch near the handle of the Big Dipper. It is a boring patch of sky. To ground-based telescopes, it is completely black. It is a hole in the universe. It is the perfect place to test the limits of the machine. The decision is made. In December 1995, while the world on Earth prepares for Christmas, Hubble will turn its back on the bright lights of the galaxy. It will aim its new, perfect contact lenses at the void. It will open its shutter, and it will wait. It will catch the rain of photons that have been falling for billions of years, unnoticed, unloved, unseen. It is about to take the most important photograph in the history of the human race. But that is the story for the next part of our journey. Let us float here for a moment. Beside the telescope, it is silent. It is steady. The solar panels glow with a soft blue light. Below, the Earth turns. The clouds drift. Above, the universe waits. The eye is open. The glasses are on. And the darkness is about to speak. December 18th, 1995, on Earth, the Northern Hemisphere is settling into winter. In the cities, people are rushing through the cold streets, buying gifts, hanging lights, preparing for the holidays. It is a time of noise, of commerce, of bright, artificial lights pushing back the dark. But 340 miles above the surface, in the vacuum of low Earth orbit, there is a different kind of celebration beginning, a celebration of silence. The Hubble Space Telescope is about to do something that many scientists considered a waste of time. It is turning its back on the showy objects of the universe. It is turning away from the bright planets. It is ignoring the colorful nebulas. It is slewing its massive body toward a tiny, nondescript patch of sky just above the handle of the Big Dipper in the constellation Ursa Major. To the naked eye, this spot is empty. To ground-based telescopes, this spot is empty. It is a black hole in the map of the stars, a void, a place where, seemingly, nothing exists. The area is incredibly small. Hold a grain of sand between your fingers. Now extend your arm all the way out and hold that grain of sand up against the night sky. The patch of darkness Hubble is looking at is the size of that grain of sand. It is 1/24 millionth of the total sky. Bob Williams, the director who ordered this observation, is gambling his reputation. He is betting that if we look hard enough, if we look long enough, the nothingness will reveal itself to be an illusion. He is betting that the dark is not empty, it is just deep. The command is sent: acquire guide stars. The telescope's fine guidance sensors lock onto two faint stars at the edge of the field. These are the anchors. For the next 10 days, Hubble must remain absolutely frozen. It is orbiting the Earth at 17,000 miles per hour. It is heating up in the sun and freezing in the shadow every 90 minutes. The metal of the hull is expanding and contracting. The atmosphere below is dragging at it with invisible fingers of gravity. And yet it must not shake. If it moves even a fraction of the width of a human hair, the image will blur. The long exposure will be ruined. It is like holding a laser pointer in Washington, D.C. and keeping the dots steady on a dime in Boston while riding a roller coaster. The gyroscopes spin, the reaction wheels hum. The telescope freezes in space. The shutter opens. The long stare begins. Let us think about the physics of what is happening inside the camera. We are used to photography being instant. You press a button on your phone and click, you have an image. That works because there is plenty of light. The sun, a lamp, a flash, they flood the sensor with photons. But looking at the deep universe is different. There is almost no light. The objects Hubble is looking for are so far away that their light has spread out over billions of light years. By the time the light reaches Earth, it is not a stream. It is a mist. It is a drizzle. Imagine you are standing in a desert during a drought. You have a bucket. You want to fill the bucket with rain, but it isn't raining. There is just a single drop falling from the sky once every hour. If you put the bucket out for a second, you will catch nothing. If you put it out for a minute, you will catch nothing. But if you leave the bucket there for 10 days, slowly, drop by drop, the water will accumulate. Hubble is a light bucket. The mirror collects the photons, the raindrops of light, and funnels them into the CCD sensor. The sensor is a grid of pixels. When a photon hits a pixel, it knocks an electron loose. It creates a tiny electrical charge. Ping, one photon. Silence, ping, another photon. It is a slow, agonizing process of accumulation. Hubble takes 342 separate exposures over 10 days. It takes pictures in blue light, in red light, in infrared light. Each time the shutter closes, the data is stored, orbit after orbit, day after day. Christmas comes and goes. The engineers at the Space Telescope Science Institute go home to their families, eat their dinners, open their presents. But the machine never sleeps. It hangs in the void, staring unblinkingly into the abyss. It is performing an act of archaeological excavation. It is digging into the fabric of the sky. Why does it take so long? Because light takes time to travel. This is the most profound concept in astronomy. When you look at the stars, you are not seeing them as they are now. You are seeing them as they were. Light travels at 186,000 miles per second. It is fast, but it is not infinite. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. If the sun exploded right now, we wouldn't know for 8 minutes. We would still see the ghost of the sun shining in the sky. When you look at Jupiter, you are seeing it 40 minutes ago. When you look at the nearest star, Proxima Centauri, you are seeing it 4 years ago. As you look deeper, you look further back. The Andromeda Galaxy is 2.5 million years in the past. We see it as it was when early humans were just learning to use stone tools. But Hubble is looking much deeper. Hubble is looking for the light that left its source when the universe was young. It is looking for first light. The light from these distant galaxies has been traveling for billions of years. It has crossed the expanding universe. As space expands, the light wave gets stretched. It turns from blue to red. This is called redshift. The further away an object is, the redder it looks. Hubble is hunting for these faint red ghosts. It is a time machine. It is trying to see the baby pictures of the universe. January 1996. The 10 days are over. The shutter closes for the last time. The telescope slews away to look at something else. The data is downloaded. It is not a single picture. It is a mess of digital files. There are black and white frames. There are frames full of cosmic rays, streaks of light caused by radiation hitting the camera. There is noise from the background glow of the Earth's atmosphere. The scientists have to clean it. They have to stack the images. Like shuffling a deck of cards, they layer the 342 exposures on top of each other. This increases the signal and reduces the noise. If you have one faint picture, it looks grainy. If you stack 300 faint pictures, the grain disappears and the detail emerges. They combine the colors. They map the blue filter to blue, the red to red, the infrared to green. It takes weeks of processing. Finally, the composite is ready. Bob Williams and his team gather around the monitor. They are about to look at the answer. Remember, they pointed the telescope at nothing, a blank black square. They expected perhaps to see a few faint dwarf galaxies, maybe some dust. They hit the key. The image loads. There is a moment of silence in the room that is heavier than gravity, a moment where the human brain tries to comprehend a new scale of reality. The screen is not black. It is exploding with light. It is a jewelry box spilled onto black velvet. Everywhere they look, there are shapes, spirals, ellipses, irregular blobs, lines, dots. There are colors, brilliant blues, golden yellows, deep rusty reds. They count them. In this tiny grain of sand, in this one insignificant, empty patch of sky, there are 3,000 galaxies, not stars, galaxies. Each of those specks of light is a city of stars. Each spiral contains 100 billion suns. Each elliptical contains 1 trillion suns. They are everywhere. They are overlapping. They are crowding the frame. It is a core sample of the universe, just as a geologist drills a core into the ice of Antarctica to see the layers of history. Hubble has drilled a core into the cosmos. The image shows galaxies at different distances, which means it shows them at different times. The large, bright, beautiful spirals are the nearby ones. They are only 1 billion light years away. They are like our Milky Way, mature, structured, adult galaxies. But look between them. Look at the background. There are tiny red smudges, little dots of crimson light. These are the ancients. These are galaxies that are 10, 11, 12 billion light years away. We are seeing them as they were just after the Big Bang. They are the toddlers of the universe. They are messy, chaotic, clumping together to form larger structures. We are watching the construction of the universe in a single static image. The Hubble Deep Field image was released to the world. It changed everything. It didn't just change astronomy, it changed philosophy. Before this image, we could only guess how many galaxies were in the universe. We had theories, but no proof. Now, we could do the math. The scientists took that single grain of sand. They counted the 3,000 galaxies inside it. Then, they calculated how many grains of sand it would take to cover the entire sky. The answer is about 40 million. So you take 3,000 and multiply it by 40 million. The result is 120 billion. That was the lower limit. The deep field proved that there are at least 120 billion galaxies in the observable universe. Later, deeper images would push that number to 200 billion, then 2 trillion. Think about that number. 2 trillion galaxies. Each galaxy has, on average, 100 billion stars. That means there are more stars in the universe than there are grains of sand on all the beaches of Earth combined. Take every beach in the world, Copacabana, Bondi, Miami, the Sahara Desert. Count every single grain of silica. There are more stars than that. And around those stars there are planets. If only 1 in a billion has a planet like Earth, there are still billions of Earths. The deep field destroyed the idea of human centrality forever. We are not just a speck in a large room. We are a speck in a room so filled with other specks that the mind cannot hold the concept. And yet there is a paradox. Looking at this image does not make you feel insignificant. It makes you feel connected. Because we built the machine. We, the little creatures on the little rock, figured out how to polish the glass, how to launch the rocket, how to hold the camera steady for 100 hours. We are the universe looking at itself. We are the eyes of the cosmos. Let's look closer at the image. Let's drift into it. Imagine you are floating inside the deep field. You are passing a large spiral galaxy in the foreground. It looks like a pinwheel of blue fire. Those blue knots in the arms, those are nurseries. Vast clouds of hydrogen gas where new stars are being born right now, or rather, 1 billion years ago. Inside those nurseries, solar systems are forming. Planets are, maybe life is starting in the primordial oceans of a world orbiting a blue star past that galaxy. Go deeper, you see a yellow elliptical galaxy. It looks like a fuzzy ball of wool. This is an old city. The stars here are ancient red giants. The gas is gone. No new stars are being born. It is a retirement home for suns. It is quiet there. Stable. 1 trillion old stars humming in the dark. Go deeper still. You see strange shapes. Train wrecks. 2 galaxies colliding. They are passing through each other. Gravity is ripping long streamers of stars out of them, creating tails that stretch for light years. It looks violent, but it is a silent dance. The stars are so far apart they don't hit each other. They just pass like ghosts. But the gas clouds collide. They compress. They ignite a firestorm of star birth. This is how galaxies grow. They eat each other. Our own Milky Way is a cannibal. It has eaten smaller galaxies in the past. And in 4 billion years, it will collide with Andromeda. We are seeing our own future in the past of these distant worlds. And then, the red dots, the background. These are the most mysterious of all. They are so far away that their light is barely a whisper. They are the first cities. They formed when the universe was only a few 100 million years old. The darkness of the Dark Ages was just ending. The first stars were switching on, like lights in a house at dusk. Looking at these red dots is like looking at a photo of your great-great-grandparents. You don't know their names, you don't know their stories, but you know that without them you wouldn't be here. The atoms in your body, the carbon in your cells, the iron in your blood, the calcium in your bones, were forged in the hearts of stars like these. When these ancient stars died, they exploded. They scattered their ashes into the cosmos. That ash formed new clouds. Those clouds formed new stars. And eventually, one cloud formed the sun and the earth and you. The Hubble Deep Field is a family photo album. It is a picture of where we came from. But the scientists weren't satisfied. They wanted to go deeper. In 2004, they did it again. They created the ultra-deep field. They pointed the telescope at a different patch of sky. In the constellation Fornax, they stared for 11 days. They used a new camera, the advanced camera for surveys. installed by astronauts on a later mission. The result was even more staggering. They saw 10,000 galaxies in a spot of sky the size of a straw hole. They saw back to within 800 million years of the Big Bang. Then, in 2012, they did the extreme deep field. 23 days of exposure, 2 million seconds of light collection. They saw galaxies that were just 400 million years old. They were scraping the bottom of the barrel of time. They were running up against the physical limit of what Hubble could see. As the universe expands, the light from the very first stars is stretched so much that it turns from visible light into infrared. Hubble can see a little infrared, but not enough. The light from the beginning of time is invisible to its glass eyes. Hubble had taken us to the edge of a cliff and showed us the fog below. It told us there is more down there, but I cannot see it. To see the rest, to see the very first star that ever shined, we would need a new machine. A machine with golden eyes. A machine that is cold. A machine that sees heat instead of light. We needed the successor. We needed the James Webb Space Telescope. But that is the future. Let us stay in 1995 for a moment. Let us sit with Bob Williams and his team in the dark room in Baltimore. Let us feel the weight of the realization. Before the deep field, the universe felt vast, but maybe empty. A few islands of light in a lonely ocean. After the deep field, the universe felt crowded. It is teeming. It is overflowing. There is no empty space. Every direction you look, no matter how dark, no matter how small, ends in a galaxy. If you had eyes powerful enough, the night sky would not be black. It would be a solid wall of light, a tapestry of spiraling worlds overlapping each other forever. The darkness is just a limitation of our eyes. The reality is light, infinite, endless light. So tonight, as you close your eyes, imagine that grain of sand held up to the sky. Imagine the 3,000 galaxies swirling inside it. Imagine the trillions of worlds orbiting those stars. Imagine the sunrises on those worlds. Blue suns, red suns, twin suns. Imagine the oceans, the mountains, the clouds. Are there eyes looking back at us? Are there astronomers on a planet in the Andromeda galaxy, pointing their telescopes at the Milky Way? Do they see our galaxy as a beautiful spiral? Do they wonder if they are alone? The light from our sun, the light reflected off our Earth, is traveling towards them right now. We are sending our own deep field image out into the cosmos, one photon at a time. We are part of the picture. We are not the observers. We are the observed. We are just another speck of light in someone else's telescope. And there is a strange comfort in that. We are not lost. We are just tucked away. One pixel in the grandest image ever made. Time is the one force that even the most perfect machine cannot escape. By the late 2000s, the Hubble Space Telescope was showing its age. It had been orbiting the Earth for nearly 20 years. It had traveled more than 3 billion miles. The harsh environment of low Earth orbit is a slow-motion sandblaster. Micrometeoroids, tiny grains of dust moving at bullet speeds, had pitted the silver skin of the telescope. The thermal blankets, once crisp and shiny, were flaking and peeling like sunburned skin. Inside, the electronics were dying. The gyroscopes, the spinning wheels that kept the telescope steady, were failing one by one. The batteries were losing their ability to hold a charge. The backup computer had short-circuited. Hubble was becoming senile. It was losing its balance. It was losing its memory. NASA faced a difficult choice. The space shuttle fleet was scheduled to be retired. It was too dangerous, too expensive. The plan was to let Hubble die, to let it drift until gravity pulled it down into the atmosphere, where it would burn up in a streak of fire over the Pacific Ocean. But the public refused to let it go. School children wrote letters. Astronomers lobbied Congress. The telescope had become more than a scientific instrument. It was the People's Telescope. It was the eye through which we all saw our place in the universe. So one last mission was approved. One final house call. STS-125. The Space Shuttle Atlantis. It would be the most dangerous complex repair mission ever attempted. May 2009. 7 astronauts launched into the blue sky of Florida. They knew this was the goodbye tour. They were not just fixing a machine. They were preparing it for a lonely retirement. They caught the telescope with the robotic arm. They pulled it into the cargo bay. For 5 days, they performed surgery. They installed new batteries. They installed new gyroscopes. They installed a new camera, Wide Field Camera 3, that could see deeper into the infrared. But the mission was not smooth. During one of the spacewalks, astronaut Mike Massimino encountered a nightmare. He needed to remove a handrail to access a broken power supply. He put his power tool on the bolt. He pulled the trigger. The bolt didn't turn. It stripped. The head of the bolt was sheared off. The handrail was stuck. If he couldn't remove it, he couldn't fix the power supply. The instrument, the Space Telescope Imaging Spectrograph, would remain dead forever. Mission Control went silent. They had no procedure for this. Massimino floated in the vacuum looking at the stripped bolt. He was frustrated. He was scared. The engineers on the ground went to a test lab. They tried everything. Finally, they came back with a solution that went against every rule of spaceflight. "Mike," they said, "we want you to rip it off." "Rip it off?" "Yes. Tape up the metal so no debris flies out. Grab the handle and pull until it breaks." Brute force in a spacesuit on a billion-dollar instrument. Massimino taped the rail. He braced his feet. He grabbed the handle with his bulky, gloved hands. He pulled. He channeled all the frustration, all the hope, all the strength of the human species into that one motion. Snap, the metal sheared. The rail came free. Massimino held the broken piece of metal in his hand. He breathed a sigh of relief that fogged his visor. He fixed the instrument. It was a reminder that space exploration is not just about math and clean rooms. Sometimes it is about sweat and muscle and the stubborn refusal to accept defeat. On the final day, the crew finished their work. They installed a special device on the bottom of the telescope, the soft capture mechanism. It is a metal ring. It has no function for science. It is a handle. It is there so that 10 or 20 years from now, a robotic spacecraft can fly up, grab Hubble, and gently push it into the atmosphere to destroy it safely. It is a tombstone installed while the patient is still alive. The astronauts floated back into the shuttle. The robotic arm lifted Hubble out of the bay one last time. Commander Scott Altman fired the thrusters. Atlantis backed away. The crew crowded around the windows. Hubble hung there, shining in the sun. It looked brand new. It was more powerful than it had ever been. "It's beautiful," someone whispered. They watched it get smaller. It turned into a silver star, then a dot. Then it vanished. That was the last time human eyes ever saw the Hubble Space Telescope. Since that day in 2009, it has been alone. No more visits. No more repairs. If a gyroscope breaks now, it stays broken. If a camera fails, it stays blind. It is drifting on its own, fighting the entropy of the universe, sending down pictures of glory until the very end. But as Hubble sailed on into its twilight years, a successor was being born. Hubble had a limitation. It could see visible light, the same light our eyes see, and it could see ultraviolet, but it could not see the beginning. Remember the deep field? The tiny red dots? Those were the oldest galaxies Hubble could see. But the light from the very first stars, the ones that ignited right after the Big Bang, has been stretched so much by the expansion of the universe that it is no longer visible light. It has become infrared, heat. To see it, you don't need a glass mirror. You need a gold mirror. and you cannot be warm. Hubble orbits the Earth. The Earth is warm. The Earth radiates heat. Trying to see faint infrared light while orbiting the Earth is like trying to see a firefly while standing next to a bonfire. To see the beginning of time, the new telescope had to go far away. It had to go to a place called L2, the second Lagrange point, 1,000,000 miles from Earth, 4 times further than the Moon. A place of eternal cold, a place where the shadow is permanent. The successor was named the James Webb Space Telescope. If Hubble was a school bus, Webb was a tennis court. It was too big to fit in a rocket. So, the engineers had to design it to fold. Like a giant golden origami flower, it had to fold up to fit inside the fairing of an Ariane 5 rocket, and then unfold itself in space. It was the most complex sequence of movements ever designed. There were 344 single points of failure. If one latch stuck, if one cable snagged, if one motor froze, the telescope would be a $10 billion piece of space junk. There was no space shuttle to go fix it. It was too far away. It had to work perfectly. The first time. It took 20 years to build, 20 years of delays, 20 years of budget overruns, 20 years of people saying, "It will never work. It is too complicated. It is too fragile." But the engineers persisted. They tested it in vacuum chambers. They shook it. They froze it. They polished the mirrors. This time, the mirrors were not glass. They were beryllium, a light, strong metal. There were 18 hexagons, coated in a microscopic layer of pure gold. Gold is the best reflector of infrared light. It was a honeycomb of gold, waiting to catch the heat of the first stars. Christmas Day 2021. The world watched. In French Guiana, on the edge of the jungle, the rocket waited. It was a perfect morning. The sky was overcast, but the winds were calm. Décollage. Liftoff. The rocket rose. It punched through the clouds. It carried the hopes of 10,000 astronomers. It carried the curiosity of 8 billion people. It released the telescope on a perfect trajectory. And then, the long dance began. For 2 weeks, as Webb traveled toward its dark parking spot 1,000,000 miles away, it began to unfold. First, the sun shield. 5 layers of kapton, thin as a human hair, the size of a tennis court. It had to tension perfectly to block the heat of the sun. We watched the telemetry. Layer 1 tensioned, Layer 2 tensioned. One by one, the layers tightened. Then, the secondary mirror, a tripod that had to swing out and lock. Click, locked. Then, the golden wings. The side panels of the main mirror folded out. Click, click. It was a perfect performance. A mechanical ballet in the silence of deep space. The telescope arrived at L2. It cooled down. It reached -380 degrees Fahrenheit. It was cold enough to see the heat of a bumblebee on the moon. It opened its golden eye, July 11th, 2022. The first image. Just like with Hubble, the director decided to look at a deep field. They pointed Webb at a cluster of galaxies called SMACS 0723. Hubble had looked at this spot for weeks to get a faint image. Webb looked at it for 12 hours. The image was released at the White House. It was overwhelming. The background was not black. It was crowded. It was a riot of galaxies. But they looked different. Because of the massive gravity of the galaxy cluster in the foreground, space itself was bent. It acted like a lens, a gravitational lens. The distant galaxies in the background were stretched. They looked like arcs of light. They looked like taffy being pulled. They were warped, distorted, magnified by the gravity of the cluster, and they were red. So red, Webb was seeing galaxies that existed 13.1 billion years ago. It was seeing the universe when it was a toddler. The detail was impossible. We could see star clusters inside galaxies that were at the edge of the known universe. We were seeing light that had traveled for 95% of the age of the cosmos. Hubble had shown us the ocean. Webb was showing us the drops of water. Hubble and Webb are not rivals. They are siblings. Hubble sees the visible light, the blue and the green. Webb sees the invisible, the infrared. Together, they give us a complete picture. Hubble as the old master, painting with oil. Webb as the digital architect, rendering in hyper-realism. Today, they are both up there. Hubble is in low Earth orbit, skimming the atmosphere, watching the weather on Jupiter, watching the aurora on Saturn. Webb is far out in the dark, 1,000,000 miles away, with its back to the Earth, staring into the deep past. They're the two eyes of humanity. One eye looks at where we are, the other looks at where we came from. But what is the legacy of all this glass and gold? Why do we build these machines? We build them because we are terrified of the dark. For most of human history, the night sky was a ceiling. It was a dome with pinpricks of light. We made up stories to explain them. We drew bears and hunters and gods in the stars because we couldn't stand the idea that they were just fire and gas. We wanted them to be about us. The telescopes taught us humility. They showed us that the universe is not about us. We are not the center. We are not the point. We live on a dust mote orbiting a mediocre star in the suburbs of a spiral galaxy that is just one of 2 trillion galaxies. To some, this is frightening. It makes them feel small, meaningless. But there is another way to look at it, a way that brings peace. Think about the light. Think about a photon leaving a star in the Andromeda galaxy. It travels for 2.5 million years. It crosses the intergalactic void. It dodges dust clouds. It flies through the vacuum. It enters our solar system. It passes Pluto. It passes Jupiter. It enters our atmosphere. It passes through the clouds. It enters the telescope. It bounces off the mirror, and it lands on a pixel. Or it lands on your retina. You are the destination. The universe has spent billions of years sending messages, and for the first time in 4.5 billion years, there is someone here to read them. We are the universe waking up. We are the way the cosmos knows it's. Without us, without our eyes, without our telescopes, the universe would be vast, but it would be unobserved. It would be a play performed in an empty theater. We are the audience, and the show is magnificent. Let us pull back now. Let us leave James Webb at its lonely outpost, its gold mirrors shivering in the cold. Let us leave Hubble in its orbit, its silver skin scarred by time, spinning silently around the home world. Let us drift further out, past the moon, past the planets, past the Voyager probes in the interstellar dark. Imagine the entire universe as a breathing organism, expanding, cooling, creating, galaxies spinning like wheels, stars igniting like sparks in a bonfire. It is a slow, rhythmic dance. It is not chaotic. It is harmonious. There is a rhythm to the orbits, a rhythm to the light. Breathe in that rhythm. Feel the expansion in your own chest. You are made of the same stuff as those mirrors. The atoms in your eyes were forged in the same fires as the gold on the telescope. You belong to this darkness. You belong to this light. In a few years, Hubble will fall. Gravity will finally win. The atmosphere will catch it. It will turn into a shooting star, a final burst of glory over the ocean. Its atoms will scatter into the wind. They will fall into the water. They will become part of the earth again. The cycle will close. But the images will remain, the pillars of creation, the ultra-deep field, the eye of God. They are burned into our collective memory. They have changed us. They have widened our view from a keyhole to a panorama. We are no longer prisoners of the sky. We have broken the ceiling. The universe is open. The door is unlocked. and we have just stepped across the threshold. The telescopes are watching. They never blink. They never sleep. They stand guard against the ignorance of the past. They hold the light for us so that we can rest. So you can sleep now.